Hello and welcome to this video about a conductor in an electric field. Here we have a small charged particle that's coloured magenta, which is a dark pink, which emits a lot of electric field lines, and a good conductor which is coloured green and which influences these lines. I'll show you how to write a computer program that can find the charge distribution in this conductor and thus draw these lines of electric field, and even to find the function which describes the charge distribution in this conductor. Here is a diagram of this same electric field, but with arrows displaying the field instead of lines. Notice that the field isn't zero inside the conductor as it ought to be, due to the charge distribution not having enough accuracy. So here is the charge distribution in this conductor. Notice where the different charges are. I use different colours for positive and negative charges. So now to find the distribution of electric charge on the surface of a circle. I'll be doing these calculations in 2 dimensions instead of 3, so as to make the calculations easier to follow. These calculations can be adapted to 3D. We'll make some assumptions. Firstly, that all of the charges are on the surface, and that there is zero charge inside the circle. Secondly, that all of the electric fields are perpendicular to the conductor when they are a very tiny distance from it. And thirdly, that the total net electric charge of the conductor is zero. So this is a calculation of the electric field at one point due to an electric charge at another point. The electric field is the point that the small red arrow points from, and the charge is a small grey circle. The electric field point is indexed by the variable I, and the electric charge point is indexed by J. So this is the formula for the distance squared between these 2 points. And this is the formula for the distance. And this is the formula for the cube of this distance, which we'll be using. And so this is the angle theta that is associated with the electric field point and can be indexed by I. And we can use this angle to find the unit vectors for the tangent and normal for these surface charges, which will correspond to the electric field point. And so this is the x component of the electric field for this electric field point. And it may be simplified to be this. And the y component of this electric field may be similarly found. And so this electric field may be rewritten in this form, where the x and y components are separated. And then it may be multiplied by the unit tangent vector using dot product multiplication. And so this is the tangential component of the electric field, and the total of this should be 0, because it is extremely close to a good conductor, but it isn't 0 yet, because it hasn't been totaled yet. So we'll just write this out again, and we'll get the total of all these tangential components of the electric field, and this total should be equal to 0, because it is nearly touching a good conductor. And we can write it out like this, taking the constant k outside the sum. And we can divide both sides by k, thus eliminating it. And we have to include the external charge in this sum. And we include it in the sum by writing it up the top of the summation symbol. And we can set this function to be equal to this complicated mathematical expression to make the rest of these calculations easier to follow. And so we can write out this sum much more simply. And we can write it out like this using dot notation. And we can bring the external charge part of the expression over to the other side of the equation, because its charge is already known. And we can rewrite this in matrix notation like this, because we're going to find all the values of Q using a matrix. So we'll just rewrite this expression at the top to keep things neat and tidy. We'll find more of these equations for different locations of electric field very close to the surface of the conductor. And we'll use the fact that the conductor has zero net charge on its surface, so that all of these Q's equate to zero. And we'll write this down again in dot notation. We'll just write this out again. We'll add this line to the top of this matrix, since it can be used to help solve for the surface charge distribution, which are the values of Q. In fact, it's a necessary condition. They must equate to zero. We'll need to make this matrix square so that it may be solved uniquely with only one set of values for Q. We do this by setting m equal to n minus 1. And so this is what the final matrix will look like. So we'll find n values of Q for n minus 1 locations of electric field. This will give us a noticeable gap if we want to locate these fields between the electric charges. You could use a slightly different angle for the electric fields so that they more uniformly cover the surface, but it doesn't really make that much difference. It is a good idea to have a distribution with a gap for smaller amounts of charge, so the field sits nicely in the middle of the charges. Another idea is to have more locations of this charge, so that the charge will be more spread out, but having groups of about 6 or more having the same charge. This will make the charge more finely spread out, without making the matrix grow too large and having problems associated with a large matrix, like for it to take a long time to be solved and being filled with errors. So this would be the new term for Fe in the matrix that we calculated earlier. It looks complicated, but will only be calculated once before it is inserted into the matrix to be solved, and should give a more accurate solution. And all these charge locations will have the same amount of charge in them. The second indices on x and y are a reference to which of these locations that this equation is referring to for a particular charge of Q. And this is a look at the matrix again, so as to see where all these values of Fe go. Sorry about the clutter on the screen. It's very difficult to display all of this at once. So now to draw the lines. For these continuous field lines, start from the point charge, then calculate the direction of the field, then calculate the next position by going a small distance from this point in this direction, and draw a small segment. Then repeat this step until you get out of the picture or you're inside the conductor. The field lines coming out of the conductor need to start from there. These lines are calculated to be blacker when the electric field is stronger. These electric fields need to be calculated using every point charge that is given or calculated, all added together. And to draw the arrows, you'd need a set of nested loops to draw an arrow from every point in a grid. And you can even try to find the function that describes the distribution of charge as a function of angle. Here is the function that I found for this distribution using interpolation. And I calculated this quantity, which measures the accuracy of this polynomial, by subtracting the calculated value for a given angle from the value given by this polynomial. And I got this range of values, which showed this function to be inaccurate for values close to 3. But this polynomial has a degree of 20, so it's very difficult to make it accurate for these values. I decided to calculate another polynomial type function for it, being one polynomial divided by another. I've shown it here. and here is a list measuring its accuracy, and it seems to be a lot better than the last polynomial function. I'll just include these charge values for completeness. So I hope that this video has been helpful for you, and I wish you all the best in your quest to study this subject.